Why do elements show trends in the periodic table? It all comes down to how electrons are arranged in atoms, and how those arrangements repeat in a predictable way as you move across or down the table. Let's start with the basics. Every element has a unique atomic number, which tells you how many protons are in its nucleus. In a neutral atom, that also tells you how many electrons it has. Now, electrons don't just float around randomly. They occupy specific energy levels, called shells, and within those shells, they fill subshells and orbitals in a very specific order. This is dictated by quantum mechanics. The first shell holds up to 2 electrons, the second up to 8, the third up to 18, and so on. But within each shell, electrons fill the s, p, d, and f orbitals in a particular sequence. For example, in period 2 of the periodic table, lithium has 3 electrons, 2 in the 1s orbital and 1 in the 2s. Beryllium has 4, 2 in 1s, 2 in 2s. Boron adds 1 to the 2p orbital. This continues until neon, which has a full second shell, 1s squared, 2s squared, 2p6. Once that shell is full, the next element, sodium, starts a new shell. This repeating pattern of electron configurations is what makes the periodic table periodic. It's like musical octaves. The notes repeat, but at a higher pitch. And just like musical notes define the character of a song, electron configurations define the chemical behavior of elements. Now, let's talk about what actually causes the trends we see. The key idea is effective nuclear charge, or ZF. This is the net pull that the nucleus exerts on the outermost electrons. It's calculated as the number of protons, Z, minus the shielding effect, S, from inner electrons. So, ZF equals Z minus S. Across a period, Z increases by 1 with each element, but the added electrons go into the same shell, so shielding doesn't increase much. That means ZF increases, and the outer electrons are pulled in more tightly. Down a group, Z also increases, but now the electrons are added to new, more distant shells. Shielding increases significantly, so ZF doesn't rise as much, and the outer electrons are held more loosely. Think of the nucleus as a magnet and the electrons as metal balls. Inner electrons act like insulation, reducing the magnetic pull felt by the outer ones. Now, let's apply this to the major periodic trends. First, atomic radius. That's the size of the atom, or how far the outermost electron is from the nucleus. Across a period, atomic radius decreases. Why? Because ZF increases, pulling electrons in closer. Down a group, atomic radius increases. More shells are added, so electrons are farther out. Second, ionization energy. This is the energy needed to remove an electron. Across a period, it increases. Electrons are held more tightly, so it takes more energy to remove them. Down a group, it decreases. Electrons are farther from the nucleus and more shielded, so they're easier to remove. Third, electronegativity. That's how strongly an atom pulls shared electrons in a bond. Across a period, it increases. Down a group, it decreases. Fluorine is the most electronegative element. Francium is one of the least. Fourth, electron affinity. That's the energy change when an atom gains an electron. Across a period, it becomes more negative. Atoms want to gain electrons to complete their shells. Down a group, it becomes less negative. Larger atoms don't attract extra electrons as strongly. Fifth, metallic character. That's how easily an atom loses electrons. Across a period, metallic character decreases. Down a group, it increases. That's why cesium is more reactive than lithium, and why chlorine is more reactive than iodine. Now, why do elements in the same group behave similarly? Because they have the same number of valence electrons. Group 1 elements all have 1 electron in their outermost s orbital. That's why lithium, sodium, and potassium all form +1 ions and react violently with water. Group 17 elements all have 7 valence electrons, 2 in the s orbital and 5 in the p. They all want 1 more electron to complete their octet, so they're highly reactive nonmetals. Group 18 elements have full outer shells, making them stable and unreactive. But not all trends are perfect. There are exceptions, and they make sense once you dig deeper. For example, beryllium has a higher ionization energy than boron, even though it comes before it. That's because beryllium's outer electron is in a 2s orbital, which is lower in energy and more tightly held than boron's 2p electron. Another example. Nitrogen has a higher ionization energy than oxygen. That's because nitrogen has a half-filled 2p subshell, which is relatively stable. Oxygen has one paired electron in a 2p orbital, and that pairing causes repulsion, making it easier to remove. Transition metals and intertransition metals also show irregular trends. That's because D and F electrons don't shield well, and their energies are close together. This leads to multiple oxidation states and less predictable behavior. In the lanthanides, poor shielding by 4f electrons causes the so-called lanthanide contraction. Atomic radii shrink more than expected, affecting the elements that follow. Finally, in very heavy elements, relativistic effects come into play. Electrons move so fast that their mass increases, and this changes orbital shapes and energies. That's why gold is yellow and mercury is liquid at room temperature. These effects tweak the trends, but they don't break them. They're just more complex applications of the same principles: electron configuration, effective nuclear charge, and shielding. So, to sum it all up, elements show trends in the periodic table because increasing atomic number leads to repeating electron configurations. These configurations determine how strongly electrons are held, how easily they're lost or gained, and how atoms bond. The periodic table isn't just a list, it's a map of atomic behavior, shaped by the rules of quantum mechanics and the forces inside the atom.